Hi, so today's lecture is in continuation with IS code method for determination of bearing capacity, and we are starting with numericals. Before we start attempting the numericals which have appeared so far in Boy University examinations, we will solve some simple examples from your textbook which are in line with the set problems. Okay, so let us first start with simple numerical, and you will need IS 6403/1981, so you can please see that it's handy with you. You will find it in the IS code app that we will be using during our lectures. Okay, you have to go to the tab Foundations. In Foundations, right below, probably a third last or fourth last code that is listed is IS 6403, so keep it open. Okay, so now this is an example from your textbook that I have taken. Okay, a rectangular footing has a size of 1.8 by 3 meters, has to transmit the load of a column at a depth of 1.5 meters. Calculate the safe load which the footing can carry at a factor of safety of 3 against shear failure. Use IS code method. The method is very clearly mentioned in this problem. If it's not mentioned, then you are free to choose whichever you feel is appropriate. Any one of the methods that you studied. The soil has following properties. Porosity is given as 40%. Specific gravity is 2.67. Moisture content is 50%. Cohesion is 8 kN per meter square. And angle of friction is 32.5. Now, before we go to the solution, this problem is solved in your textbook. We will go word by word. What all information is given to you? First thing, rectangular footing is so the shape is mentioned to you. Next, the size is mentioned to you. So B and L is mentioned to you. Okay. Founding depth is mentioned to you. So it's founding depth. Some places it appears as DF, some places it appears as D. This 1.5 meter is the foundation level. Then factor of safety is given to you. Okay. Then porosity, specific gravity, moisture content, cohesion and friction. Now, before we start solving this particular problem, first decision that we need to arrive at is which is the equation for bearing capacity we are going to use. In IS code method, we have studied 4 different equations. Okay. So those 4 equations, first one for strip foundation for general shear failure, second one strip foundation local shear failure, then it was for any other foundation, okay, general shear and local shear. So we need 4 equations. Now the first question that appears in front of us is which of these equations do we follow? So for that, first question that we need to ask, is it a strip footing or strip foundation? Yes or no? No. Why? Because it's very clearly the dimensions were mentioned to us. They were somewhere around 1.8 or something, and level 3. So that clearly indicated that it's not a strip foundation. What is a strip foundation? Somewhere around the length has to be greater than 5 times width, or the width has to be more than 3 times the wall width. Just confirm this. I think I've already studied this before, but more or less it is somewhat like this. And length has to be a little bit more than equal to or more than 5 times the width, then you call it a strip. Or the width has to be more than 3 times the width of the wall that it is supporting. Okay. Now clearly it is not a strip footing. So the first equation, these 2 are clearly ruled out. Then these 2. Now, how do we know whether it's a general shear failure or local shear failure? Again, in probably our lecture number 2, that is on modes of failure, we had in the last slide there was a summary. If I'm not mistaken, it was clearly mentioned that for angular friction somewhere less than 28, you expect a local shear failure. Over here, the case is different. The angle of friction which is given to you in your numerical is somewhere around 32.5, correct? So for 32.5, we do not expect local shear failure. Understood? Do not expect the local shear failure. Now, this is what is the solution that is mentioned in your textbook. N is given, porosity is given, they have found out voids content. Why do we need voids content? Because we need the unit weight. Unit weight is not mentioned, and in your bearing capacity equation, the last term is based on unit weight. So we need to find this unit weight, bulk unit weight. So from E we obtain gamma D, that is dry unit weight, using this equation which you people are very much conversant with. So using gamma D, we are going to find a bulk unit weight. Now, once you know the bulk unit weight, for a value of 32.5, okay, we need to get the factors NC, NQ, and gamma. Okay, now this NC, NQ, and gamma, now go to your code 6403. They appear in table 1. The table 1, if I am not mistaken, is on page 8. So pause this video and go to table 1 and check if you get this particular value. Now clearly there will not be a value against 32.5. There is a value against 30 and there is a value against 35. So you need to interpolate in between. Okay? Right? So somewhere it will be obviously halfway of the difference. So interpolating, you will get the values of NC, NQ, and gamma. Then your general shear failure equation. This is also mentioned in your IS code, correct? General shear failure equation. Only this sigma will be indicated as Q. Okay? Rest everything, if I am not mistaken, is same. So we are using this equation. Now what is this IC, IQ, I gamma? These are inclination factors. So inclination factors are mentioned on page number 9. The table is on page number 8. On the next page you have the inclination factors. Now they are taken as 1. Why do we take them as 1? Because the load is vertical. Okay? That alpha mentioned, go to your IS code, pause the video and go to IS code. There is an alpha. That alpha is the angle of inclination with vertical. Okay? That the load mixed with vertical. But in this case, that angle is 0. So if that angle is 0, then directly the equation becomes, the values of IC, IQ, I gamma will become 1. Okay? And you take W dash is equal to 1. Now why do we take W dash is equal to 1? Again, go to your code, clause 5.1.2.4. Now W dash is something that depends on water table. Okay, there is no mention of where the water table lies. So what we will do, we will just assume that it is very, very deep inside. It is not going to affect our footing. If that is the case, then out of these three conditions of 5.1.2.4, A, B, C, if the water table is likely to permanently remain at or below a depth of df plus b, okay, it's much deeper, then you take W dash is equal to 1. So that is what we have assumed. Okay. Further on, we continue with this problem. Then find the shape factors. Where are the shape factors? Shape factors, you'll have to go to page number 8 again. Now what is the shape of this particular footing? It's a rectangular footing. So width given is 1.8 and the length, L is a larger dimension, B is the smaller dimension. So smaller dimension is 1.8, we take it as B. Larger dimension is 3, we take it as L. Okay. So from B and L values, we get the value of SC, SQ, S gamma. Okay. Then the depth factors. Depth factors are mentioned on 6403 on page number 9. Okay. So these equations are very clearly mentioned there. Now what is D? D is the depth of foundation which is given in your numerical as 1.5. And B is the width, the smaller dimension, that is 1.8. phi is given to you, so you calculate all these values of dc, dq, d gamma. Alright, fine. Then next is determination of effective overburden. How do we get it? Bulk unit weight into depth of foundation. So bulk unit weight we calculated as 18.07 into 1.5 is the depth of foundation which is mentioned in your numerical. Substituting all this, we get the value of Q and F. The value of Q and F, it's not visible here, so I'll just minimize it. Value of Q and F is somewhere around 1815.89. Alright, and then when you apply the factor of safety, okay, SBC. Now Q and F is what? Ultimate bearing capacity. QS is what? Safe bearing capacity. Right? So Q and F divided by F plus the surcharge gives you SBC. Safe load will be SBC into area. Okay, that is around 3415 kilonewton. So if the question is only to find the SBC, your problem ends here. If they have asked you to find what is the safe load that the foundation can take, footing of 1.8 by 3 can take, then you have to go one step ahead. Okay, so the next problem, this is from one of the question papers, going investigation. It's very similar to the one that we have solved. Of course, the values are slightly different. Over here, this is not a rectangle, it's a square footing, so your shape factor will slightly change. Specific gravity is given. Void station directly is given. In the previous case, we had velocity of 0.7. Okay, so the data more or less given is similar. Cohesion is 0. Okay, and phi value is 22. Now this is something which you have to notice. Okay, observe very carefully. Cohesion is 0, phi is 22, is 0.7. So now, what equation are we going to use? It's not a strip footing, it's a square foundation, so the first two equations are definitely ruled out. So now the next two equations of general shear failure. Okay, these are the first two equations for strip footing. For IS method, they are ruled out because that's first step. The next two equation. Now which one do we go for, general shear or local shear failure? Okay, now for C is equal to 0, let's go to this case. Okay, for C is equal to 0, E value we have been given is 0.7. And you look at this slide, it can be either general shear equation or local shear function shear equation. Now based on the data that is given to you, E value is 0.7. If it's 0.7, you can clearly see it's nearly a loose type of soil condition. If that is the case, the type of failure expected is local shear. For 0.75, it is definitely local shear. 0.7 is very close to 0.75, so I will assume that the soil is going to fail in local shear conditions. If that is the case, then I am going to use this particular equation. Rest, everything remains same. The factors n dash, nq dash, and gamma dash, how do we find these factors? These will be based on the modified value of angular friction, phi dash, which is given as tan inverse of 0.67 of phi. Phi value given to you is 22. You won't take 22 to find out n dash C or n dash Q or n dash gamma. You will take tan inverse of 0.67 times of this phi value. Then whatever is this modified phi, you will go to the same table 1 on page number 8 if I am not mistaken of IS 6403 and get the values of n dash C, n dash Q, n dash gamma. Then shape factors, then depth factors, all these things are mentioned there. Inclination factors will be equal to 1 because nothing is mentioned about inclination of load, so we will take it as vertical. So follow the same procedure to solve this particular problem. Any issues or any difficulties, get back to me. Also, I want you to go through these particular solved examples 24.1 to 24.4 of your textbook Disciplinia and 24.7 to 24.11. I have deliberately kept some out which we will study a bit later because I have taught you all those problems with some other method. Okay, so I will do it with you and then you will solve them later. Okay, So stay at home, stay safe. Bye. Hi, so continuing with numericals based on determination of bearing capacity. This is my second video, and here we are going to discuss some typical numericals on the effect of water table on determination of bearing capacity. Okay, now prerequisites. Before you start listening to this lecture, I would advise you all to see L6 video. Okay, it's necessary that you know the contents which are discussed in L6 video. Also, you need to refer certain things which we have discussed in L3 video. Okay, we will need the bearing capacity factors, NC, NQ, N gamma, and L3 video discusses Terzaghi's analysis, and in this particular lecture we are going to solve problem using Terzaghi's equations. So the bearing capacity factors are taken from a table which is displayed, which is visible in this L3 video. Also, we will need certain contents of L7. L7 is first part of IS method of determination of SVC. Okay, wherein we discuss the effect of water table. Alright, so the part where effect of water table, some three numeric equations are mentioned, somewhere around 11th minute. So you could just see that in L7 videos. Alright, so videos, please see that you have completed listening, watching, and assimilating all the information that is given by these three videos before you start listening to, before you start solving the numericals. Right? So now, this is a numerical which has appeared in your textbook. Alright, I am solving the same numerical, although the method that I have adopted here is a little different method. Alright, I am going to solve the way I have explained in the videos. See, basically I am using NPTEL notes, right? And the way we have discussed, it's pretty simple. The Terzaghi's analysis is best explained in NPTEL. Okay. However, the problems solved in your textbook are slightly longer method and a lot of memorization. You need to remember things. So I'm trying to avoid that. Okay, and NPTEL makes use of some logical explanation wherein not much of memorization is required. However, if you feel the method that is given in your textbook is simpler, you can definitely go ahead with that method. Okay, so let's start with this numerical. A split footing 2 meter wide carries a load intensity of 400 kN per square meter at a depth of 1.2 meters in sand. It's very clearly mentioned what type of sand it is. Saturated unit weight is 19.5 kN per meter cube. Unit weight above the water table is 16.8 kN per meter cube. Shear strength parameter C is equal to 0, phi is equal to 35 degrees. Determine the factor of safety with respect to shear failure for following cases of location of water table. They have enlisted 5 cases. Okay, case A is when water table is 4 meter below ground level. B is when it is 1.2 meter below ground level. C is when it is 2.5 meter below ground level. D is when it is 0.5 meter below ground level. And the last one is when the water table itself is at ground level. Now, they have clearly mentioned the method that we are going to use. They have asked to use Terzaghi's equation. Okay, so first thing I'll just enlist what is the data that is given to you. You are given the bulk unit weight, you are given saturated unit weight. C is 0, it's mentioned it is sand, plus they have again repeatedly mentioned that C is 0, phi is equal to 35, width of the foundation is 2 meters, and depth is 1.2 meters. This is what is mentioned. Alright. Also what is mentioned is Q allowable is 400 kN per meter square. Okay. Now, again, as I told you, prerequisite, you need this is using Terzaghi's equation, so you can refer the video on Terzaghi's analysis. You need the chart wherein Terzaghi's bearing capacity factors are mentioned. Alright, so you go to the chart, probably it's in L3 video, and you find out the values of bearing capacity factors. Now there are 3 bearing capacity factors, NC, NQ and gamma. Alright, but then C is given to you as 0. So since C is given to you as 0, you don't need NC value. You're going to multiply it and this term is going to become 0. But you need NQ and gamma. So you have to refer the Terzaghi's bearing capacity factors. They're there in your books, they're there in the video. You can even Google it out. You'll get the Terzaghi's bearing capacity factors in case you don't have it handy right now. Okay. Corresponding to the phi value of 35 degrees, you get NQ is equal to 44.4 and N gamma is 42.4. This is from the table. Okay. If this kind of problems appear, these factors will be given to you. Okay. Then, what is Terzaghi's equation? QF. What is QF? QF is ultimate bearing capacity. Is equal to CNC plus sigma dash NQ 0.5 B gamma N gamma. What is sigma dash? It is overburden. Right? Now, in this particular equation, the second term, I am repeating this, we have already discussed this before. The second term is going to be affected by the conditions prevailing above the foundation level. Right? This is basically going to be affected by the moisture content in the soil, which is above foundation level. Where is the foundation? What is the depth of the foundation? It's given to you in your numerical. The depth of foundation is at 1.2. So whatever are the soil condition in the top 1.2 meter layer, okay, that will be reflected in this second term. What is below the foundation level is going to be reflected in the second term. So if suppose this is saturated, one top part is saturated, this will get affected, and obviously this also will get affected. But specifically speaking, if there is water table present here, this is going to be affected. If there is no change in the density or the moisture content of the soil in the top 1.2 meters layer, then this term will not get affected. Okay. Anything deeper down, any changes deeper down below 1.2 meters, the third term gets affected, because this term is reflecting, it is dependent on the soil conditions below the footing. Is this clear? Right. So now let's go to the case 1. Water table is 4 meter below ground level. Okay. Now when it is 4 meter below ground level, alright, D plus V, what is depth of footing? 1.2. What is width of footing? 2 meters. 1.2 plus 2, 3.2 meters. D plus V is 3.2 meters. If, theory says, if the water table is anywhere deeper than D plus V, then you don't have to worry about the presence of water table at all. It will not affect the foundation. That is what the theory says. What does it say? If your water table is at a depth which is greater than D plus V, then none of the terms are going to be corrected. Hence, no corrections to gamma are required. So my equation QF, CNC becomes 0 because C is 0. Sigma NQ plus 0.5 B gamma N gamma. What is sigma? Overburden given to as depth of foundation into unit weight. So this will reduce to, this term is 0. This sigma is going to be 16.8 into 1.2. Depth of foundation is 1.2, gamma is 16.8, NQ is 41.4. This is NQ with jumbled up values. Nevertheless, it's pretty clear, I feel. Then, second term, 0.5, B is 2 meter, gamma is 16.8, and gamma is 42.4. Right? Your QF value becomes 1546.944 kilonewton per meter square. Right? And your Fs value, Fs is given as ultimate bearing capacity divided by allowable. Right? So that is, allowable is 400 meters at 400 kilonewtons per meters squared. That is mentioned somewhere here. I mentioned it. Q is 400 kilonewton per meter squared. So 1546.944 divided by 400, that gives you 3.867. That is the factor of safety. Right? Now going to the second case. Now what is my second case? My second case is water table at the base of footing. So where is my water table? Here. Right? This is my footing, and there wherever footing rests exactly at the same point, water table is also present. So now what will happen in my previous equation? If I want to go back to previous equation, where is my water table now? Here. So which of these terms will get affected? My water table is here. I told you whatever happens here will be reflected in this term. Whatever happens below this will be reflected in this term. So now clearly if my water table is here, soil above what? Above the foundation level. Soil above the foundation level will not be affected. However, the soil below, what will happen to the soil below? Water table is right here. So it's going to be submerged soil. Okay? So it will have submerged unit weight. By thumb rule, submerged unit weight was taken as saturated by 2, half of the saturated unit weight. This is a thumb rule. Exact equation is gamma dash is gamma sat minus gamma w. But we can take it as gamma sat divided by 2 directly. So now, what happens to my equation? QF, anyway the first term has gone to 0 because C is equal to 0. QF is equal to gamma D NQ plus 0.5 B gamma prime or gamma dash. What does gamma dash signify? What does it stand for? It stands for unit weight into N gamma. So if I substitute the values, here gamma is going to be 16.8. Correct? Into D is 1.2 foundation. NQ from the Kazakhstan chart is 14.4 plus 0.5 into B is 2. Gamma dash, I am taking saturated divided by 2. So 19.5 divided by 2 into N gamma. When you substitute the values, you get the answer is 1248 kilonewton per meter square. Again, factor of safety will be this particular QF divided by 400, that is allowable. That gives you 3.90. That is my case 2. Okay, so now going ahead with the problem. We are discussing the case 3, that is when the water table is present at a depth of 2.5 meters below the ground level. Now founding depth was 1.2 meters, and what is mentioned in the numerical is that water table is at 1.3 meters, sorry at 2.5 meters, so that makes it net 1.3 meters below the foundation. So I've just drawn a figure to help to understand this. Now clearly when the water table is at 1.3 meters below the foundation level, our second term of the equation is not going to be affected. Okay, that is the overburdened soil conditions are not going to be affected by water table. However, the third term, which is representing the soil conditions beneath the footing, here what happens, part of the soil will be dry and part of the soil will be submerged. So how do we take care of this? Okay. So what we do is, in this case, we find out what will be the average unit weight for the third term. Okay. So to consider the effect of water table beneath the footing, gamma average will be determined. So how do we find out this? This 1.3 meters, that is 2.5 minus 1.2. Okay. It's not directly given as 1.3. So 1.3 meters will have 16.8. Now, consider a depth of 2 meters below. See, right in the, when we were discussing the first case, what I told you, if the water table is present at a depth D plus B, okay, so you consider D below the foundation depth, that is 2 meters. Till that much depth, if water table is present, then it's going to affect my equation. If it's anything deeper than that, then the presence of water table doesn't happen. So now this B below the foundation of 2 meters. 2 meters minus 1.3, that leaves us with 0.7. So the unit weight for the 0.7 meters below this 1.3, are you understanding? I hope you are understanding from where I got this 0.7. 0.7 is when I take 2 meters below the foundation level, how much of the soil is submerged. Okay, so 2 minus this 1.3, 0.7 will be submerged soil. So we find out what is the average unit weight using this particular equation. We get it as 17.75. Substitute it back. Now this is going to be substituted only for the last term. Now the second term of the equation for random bearing capacity is not going to be affected at all by water table. Right? So my second term becomes 16.8 into 1.2 into 41.4 plus 0.5, these two, gamma average is 7.75 and gamma is 42.4 into a correction factor. Now you want to take a correction factor. This is similar to what we studied in IS method. Okay, so if the water table is below D plus B depth, then this correction factor becomes 1. If it is anywhere for this particular problem, let's take an example of this particular problem. If it's going to be 2 plus 1.2, that is anything below 3.2 meters, then this W dash is going to be 1, meaning it's not going to affect. If it is anything, if this depth is anywhere between 1.2 or less, so if this water table rises at this level or above, then this W dash is going to be 0.5. And if it is in between, like in this case, it's between the founding level and 3.2 level, then you find a factor using this equation. 0.5 into 1 plus ZW. What is ZW? ZW is the depth of water table below foundation. So in this case it is 1.3. Okay, depth of water table below footing. So 0.5 into 1 plus 1.3 by 2 gives you 8.825. You substitute it here and you get a value of QF is equal to 1455 0.5 kilonewton per meter square. Then the factor of safety, QF divided by allowable, that is 3.62. That's all. Case 4 is when water table is at 0.5 meters below ground level. Just as I was discussing, in the previous case it was somewhere in between here. Now it has, let's say the water level goes up above the footing. Now it's not going right on top, it's somewhere in between. So this 0.5 meters above the water table is going to be dry. And below the water table everything is going to be submerged. So now, beneath the footing what will be the soil? That is below 1.2 meters, what will be the soil type? Completely submerged. Above the footing, it will be partly submerged, partly dry. Right? So now, our cause of concern, this second term is of no problem. This directly gets replaced by gamma dash, that is submerged unit weight. Submerged unit weight is taken as gamma set by 2, that is 19.5 by 2 in this problem. Now, how do you get this sigma dash? How I have worked this out is each textbook will give you a different way to solve these problems. Okay, whatever is simpler, whatever is logical and doesn't make you put additional efforts to memorize things, I feel that is something that you should pick up. So how I get this sigma dash? It's basically representing the overburden condition. That is weight of the soil here, in short. So how do I get the weight of the soil? Unit weight into depth is the weight of the soil. Now, unit weight for 0.5 meters depth is 16.8. Unit weight for 0.7 meters depth is submerged, that is 19.5 by 2. So I have done the same thing. Gamma 1 D1, gamma 2 D2. Gamma 1 16.8 into 0.5. Gamma 2 19.5 by 2, that is submerged, half of saturated, into 0.7. Gives you sigma dash. Okay, that is 15.225 multiplied by NQ plus 0.5 these two. Gamma dash is again n1 by 2 into positive 1. Simple. So you get the value of QR. F is equal to QF upon QR. Right? And the last case is when the water table is at the ground level. The water table from here, when it goes on top, what happens? Entire soil is submerged. So in both these terms, wherever there is gamma, it will be substituted by gamma dash. So sigma is directly written here. Gamma dash into dnq plus half of v gamma dash into. So 19.5 by 2 into 1.34. Half into 19.5 by 2 again submerged into 40.5. QF is equal to 897.78. F is equal to QF divided by Q. Now let me do the factors. Now questions based on all these. This also includes N7 and N8 and even this current. Then what I want you all to do is take a textbook, okay, and solve all these problems. Half of these problems are solved in any case. No, I think all the problems are solved. So go through all these problems. Okay, they're different types. Don't look at the solution. Take this problem, start solving using this video. Okay, start solving. See that you are getting same answers. You will not get exact same answer. Okay, more or less same answer. Right? Then after you've done, this is a numerical that one of your classmates sent to me. This is from the question papers as appeared 4 university question papers for 12 marks. Now what is this? What does this say? Discuss the effect of shape of footing on bearing capacity. This is even there in your highest grade. Okay, highest grade will be in your facts. Anyway, just refer highest grade on the shape factors. A square footing size is given, built in a homogeneous bed of sand. Sand is mentioned, solidity is going to 0. Density is mentioned, gamma. Angle of shearing 5 mentioned as 38. Depth is 1.2. Calculate the safe load by footing. Now, how do you calculate the safe load? Okay, so you will get the value of QF. Right? QF, ultimate bearing capacity, multiplied by this area will give you the safe load. So whatever QF you have found out on this here, this if you multiply by the area will give you the safe load with a factor of safety of 3 against shear failure. Right? So what do you do once you get this? Okay, you put 3 here, you get Q allowable multiplied by area will give you the safe load. You understand it? You will get QF, factor of safety is given to you as 3. So QF divided by factor of safety will give you QA multiplied by the area that is given in this numerical will be the safe load to be carried by footing. Use IS code method. So you have to refer the previous lecture. Okay? Do all these things. Example of time you will have. Please see that you solve all the numericals. Okay? Because there are more coming. Then there will be another 10-12 numericals you have to solve based on the test conducted. So finish this in smaller installments. It becomes a little easier to complete. Okay? Stay at home. There are no questions which are coming up from your side. If at all you have, feel free to ask. Right? Alright. Take care.